Hey there, guess who's back? I am. Anyways, it's time to learn how to determine whether or not a critical number is the location of a maximum or a minimum. And so I mentioned in a previous video that this goes into the second derivative of a function, and that's exactly what I'm going to explain right now. But first, I want to talk about concavity and what that is. So let's say I have a function, x cubed, just keep it simple. And it looks like this with really dramatic curves, just so I can explain this. So concavity refers to a curve and the direction it faces. So concave down is when you have, pretend like you have a bowl in your hands and you turn it upside down. So the concave, the curve of it is going to be pointing down. So the edge is going to point towards the ground. And the opposite, when you have your bowl face up, that's like having it concave up. The concavity of it, or the curve, is facing upwards into the sky when it can hold things. You can pretend that concave up is like a bowl that can hold water, and the opposite is dumping out your water. So putting it on the graph, let's do the water. This side can hold water, and on this side, all the water falls out, which means that this side is concave down, and this side is concave up. Now you may ask the question, they're connected. At what point do I say that it's concave up instead of concave down? And that's a very good question. That's called the point of inflection. So right here is the point at which it changes, where all of a sudden we don't care about concave down because it has turned into concave up, which means that the water isn't going to be held right here. If we're using the water analogy, it would be held right here. And right here, this is the part that is concave down. At this point, it switches, and this is my concave up, and this is my concave down. That's what concavity means. Now, why is this important? It's because when you have concave down, the tip of that concave is going to be a maximum. So let me redraw this. X cubed, or a cubic function at least. This is our concave right here. The top of the concave is going to be a maximum. And right here, it's going to be a minimum. Easy as pie. We can find these locations, the x values, by taking the derivative of the function and solving for 0, finding the critical numbers of our function, which is pretty easy. But you can go a step further and take the second derivative to figure out which direction it's going to concave by finding point of inflection. So when you have a function, the first derivative or the zeros of the first derivative are going to tell you where the maximums and the minimums are. And the second derivative is going to tell you where it's concave up and where it's concave down. So let me draw this on a graph to better explain it. The idea is that when the second derivative is positive, that means you have a concave up. But let's keep it simple to start with. Boom. Okay. So this is my function. Let's pretend it's x cubed, even though we'll have a few transformations, just so I can show you what it looks like on the number line in a bit. So x cubed. So the first step is going to be, let's draw our derivative. So you already know that the derivative is 0 when there's a peak or a trough. So right here and right here is where our derivative is 0. So if I took the derivative of x cubed, and I'm going to draw my first derivative in purple, the derivative of x is going to be equal to 3x squared, which is a cubic function, actually. And it's going to look something like this. So you identify where the zeros are, which is going to be here, the trough, and the peak right here. Easy enough. And then I'm just going to draw a quadratic. Boom. Now let's reapply the same principle that I did and that I used to draw this. So you can see that this corresponds here, and this, boom, dang, corresponds here. And that's where the trough is, but this, the quadratic, also has a trough. So if we took the derivative of it, we would just find where that trough is, which is going to be right here, the bare minimum of our first derivative. And then all we have to do is draw another equation. So I'm going to find the equation of my second derivative, just to show it to you. That's going to be equal to 6x. Simple as that. Which means it's going to be a linear equation. And this is going to be at 0. So all I have to do is, they don't cross anywhere else. Yep, very good. Boom and boom. There. So I want to draw your attention to what I was saying about the point of inflection. If you look at the black, which is our normal function, x cubed, the point of inflection is right here, which coincidentally coincides with the the 0 of our second derivative. So what does this tell us? It tells us that where our second derivative is positive, that means we have a concave up. Which means, because if you have a concave up, which would be this, that means that the value at the bottom of it has to be a minimum. So I hope you can see that we found our critical number and put it right here, and because this is positive, or the green, the second derivative is positive, that means we have a minimum. And vice versa. It's negative over here, which means that in this area, it's going to be a maximum. Now let's put this on a number line. This is a really simple way to do it when you're doing your homework, where you just draw out a number line and then start putting the values on them. So we have our number line. And we know x cubed is going to be our function. And I'm just going to put some values on here. We're going to have a and b are going to be the critical numbers of f of x. So the critical numbers of f of x are equal to a and b because it has two zeros. So we're going to put those on the number line, a and b. So we know that this is going to be a maximum or minimum, which one is left to be determined. But we know that they're going to be opposite of each other because you can't have, oh, I'm going the same direction and then I do it again. It just doesn't work. I can't go like that very easily. Though there are some functions that do it. I can't lie about that. So our point of inflection I'm going to call C. And C falls directly between A and B. C. So we know that when C is positive, or to the right of C, you could say, that we have an upward inflection. So I'm going to draw an inflection upwards. And this is what I do on my homework. It makes it super simple, which means it's positive. And over here, I re-erase this to align it, it's going to be a negative inflection. And notice that I'm putting that part of it, the value, wait, no, it's positive. Yeah. The base of the curve over its x value, because that's where the minimum is going, or the maximum is going to be, because that's the critical number. So this is a downward and this is an upwards, because C crosses the x-axis and over here is positive and over here is negative. And it could be reversed. If it was negative x cubed up here, these symbols would all be reversed. And C would be heading down like this instead, which would tell us the inflection. So if you want to just test, if you have the value of C and you want to test where it goes, or which side is which, all you have to do is plug in a number that is bigger than c and less than the next number on the number line. You see, you can do this with as many numbers as you want. Many critical numbers, all you have to do is just find the zeros of each one. Because the second derivative can be a quadratic, it can be a cubic, it can be whatever you want, according to whatever problem you're solving. And that's the idea of it. That's how you use the second derivative to figure out if a critical number shows where a maximum or a minimum is. And remember that if you want to find the value of said maximums or minimums on the function, you have to plug the x value back into it. So if it says if I was given this function and the problem said, hey, solve for the value of f of x at the absolute maximum, or I mean the local maximum. And so I would find a, then I would verify that it's a maximum using my second derivative. I would plug a back into x cubed, and I would get a cubed as my local maximum. And same thing for b, and I would get b cubed as my local minimum. And then the question might ask me for my point of inflection, and then I would say that is c for my x value, and then the value of the point of inflection would be c cubed, because that's where it is on the original function. Anyways, I hope that makes sense. It doesn't get more complex than that. You just have to be able to apply it into the problems, and I highly recommend drawing out this number line. This makes it so simple, especially when you get more critical numbers on both your first and second derivative. Anyways, that's it for this. Thanks for watching.